Welcome to the first episode for the year 2025 of the Focus on Geothermal webinar series. This is a partnership between ThinkGeo Energy and Enerchange. And today we have a very interesting webinar. Our topic will be CO2 Plume Geothermal, or CPG. Now it's kind of a buzzword that I think a lot of people in the geothermal industry have heard of, but I don't think that a lot of people actually completely understand the concept. And now we have a very good turnout of people today, and so there's clearly a very high level of interest in this topic. And now there's this sort of knowledge gap about CPG, and so to kind of address this knowledge gap, we invited a speaker who is probably one of the most qualified to talk about CPG. So Professor Martin Saar is the head of the Geothermal Energy and Geofluids group at ETH Zürich. The group does research in the areas of reactive subsurface fluid and energy transfer. So this covers geothermal energy extraction and conversion to plus CO2 sequestration and combinations thereof. And so CO2 plume geothermal is one of the examples of these types of combinations. So during this webinar, we will be learning about what CO2 plume geothermal is, how it improves upon, say, the thermodynamics of hydrothermal geothermal. We'll learn about the CPG Consortium and then the future plans for this type of technology. To everyone in the audience, you are free to ask questions. There should be a questions tab somewhere in the webinar panel. And so just type in the questions there and we'll try to get to as many of the questions as we can after the presentation. And so, Martin, welcome to the webinar, and the floor is yours.
Yeah, thank you very much, Carlo. I'm very happy to have the opportunity to give this presentation here in the ThinkGeo Energy webinar series. So I'll start right away here. And this is my cover slide. So CO2 plume geothermal is something that I co-invented with two people. This is you can see on the left all the collaborators on CPG over the last 15 years. And aside from me as co-inventor, there's also Jimmy Randolph, who was a PhD student of mine at the time in 2009 when we came up with this, and Tom Keene, also at the University of Minnesota, who was a mechanical engineering professor. So you can see on the left-hand side that there have been a number of people working on CPG. I named it CO2 Plume Geothermal in San Francisco in 2009, 2010, to distinguish it from CO2 EGS, which Don Brown had suggested. And we will see also in a moment what the differences are between CPG and CO2 EGS. So today I'm going to talk about both what it does for geothermal energy extraction and increasing the resource base, and for the CCS operation that is underlying the CPG, which is basically superimposed on top of CCS operations. So this research has been funded by a number of funding resources. On the right, you can see here that the CPG Consortium has been supporting this financially and also with knowledge and data. So we have here multiple companies on the right shown, and then also my Geothermal Energy and Geofluids group here at ETH Zürich is supported also by other grants from funding agencies and by companies. So let's dive right in. Here's an outline of my presentation. I'm going to start with the CPG introduction, and then we'll look at some results here and how CCS benefits from CPG, and then we'll talk about the CPG Consortium. So a little bit about CPG, what it is, CO2 plume geothermal. So what you can see here is you have a CO2 capture facility. This does not have to be necessarily a fossil fuel power plant. It could also be a cement manufacturer or a biofuel refinery, basically any point source CO2 emitter that adds CO2 capture to its operation. And then standard CCS would be done. So you bring the CO2 underground, and normally with CCS, you leave it at that. And then with CPG, we bring the geothermally heated CO2 back up to the surface, run it through a turbine, cool it, condense it, and then re-inject it back into the subsurface, so that in the end, very importantly, all CO2 is geologically sequestered subsurface. The typical CPG reservoir would be 2 to 4 kilometers deep, so not all CCS reservoirs would apply, and the reservoir should be at a temperature of 100 to 150 degrees Celsius. So we're thinking here about standard continental crust geothermal gradients that are geothermally benign, so they're not necessarily particularly hot geothermal areas. They can be, that's even better, of course, but they don't have to be. So this is another depiction of CPG on the right here. And again, you have a CO2 emitter, it captures CO2, it goes underground, it gets geothermally heated, brought back up to the land surface, expanded in a turbine, cooled, condensed, and re-injected. So what is the big deal about using CO2 to extract geothermal energy? Basically, you get more energy out, and the reason for this is, and it's more efficient. The reason for this is that the kinematic viscosity, this is the blue number here in this little equation, is typically much higher for supercritical CO2 under the reservoir conditions that we have compared to water. So the mobility is much higher. The kinematic viscosity which is the inverse, is much lower. And this means that the thermal energy output, so the thermal energy output that comes up to the surface, is also a lot higher, all else being equal, compared to using water. So you can see here our base case is a reservoir at 2.5 kilometers depth and a temperature of 100 degrees Celsius. Roughly speaking, the mobility of supercritical CO2 is about 4 times higher than that of water. And so that means that you would get 4 times the thermal power out. However, since the specific heat capacity of supercritical CO2 under those pressure and temperature conditions is roughly half that of water, you have to multiply that factor 4 with a factor 1/2, so that leaves roughly 2 times the power output for CO2-based energy extraction compared to water-based energy extraction. So now there's also a thermosiphon effect. So this simply means that as you heat the CO2 up in the reservoir down here, it basically has a density of roughly half that of the injected liquid CO2. And so once you connect the subsurface with the surface power plant with the wells, you get a thermosiphon, so it essentially circulates on its own, the CO2. And that, of course, helps also with reducing parasitic pumping power costs. And you can also see this on the right here as you go down here with the CO2, and then the pressure, of course, increases, then the reservoir it decreases somewhat, and then as you come back up to the land surface, for example, along this green line, you still end up with a much higher pressure. So there's a lot of energy in the pressure and compared to the heat that's in the CO2 that's being produced. And of course, a turbine, which is an expander, can utilize both the pressure and the heat energy when it generates electricity. But I also want to emphasize, and I go very briefly back to the previous slide, that the equation here below you can see is for thermal energy output. So really CPG starts out with being, extracting much more energy compared to water in terms of heat and pressure energy. So even if you use the heat directly, you still have a benefit from using CO2. So here's a video that we made to explain this a little bit more. This is just 1.5.
Replacing water with carbon dioxide yields a number of benefits. First, CO2 flows more easily than water. As a result, it can extract the same amount of energy from the ground with less effort. Second, note the fluid at the injection well is under low pressure because it is cool. and the fluid at the production well is under higher pressure because it is hot. The amount of energy that can be produced is dependent on the difference in pressure between the wells. Hot water is under more pressure than cold water, and it yields a good amount of energy. But when CO2 is heated, the pressure changes much more, and the energy yield is substantially greater as a result. Third, the heated carbon dioxide expands so much that it will buoyantly rise through the production well. Scientists refer to this unique effect as a thermosiphon. This can reduce or eliminate the need to use the well pumps, and more energy can be available for the consumer. A new type of power plant, a CO2 Plume Geothermal plant, or CPG, can use the improved flow rate, the pressure difference, and the thermosiphon to generate electricity at shallower, cooler depths than is possible with water. This expands the locations where geothermal energy production is cost-effective and competitive with other sources of electricity. Plants at existing locations can also run more effectively.
So this is a video we made based on US National Science Foundation grant that we got when I was still in the US. And it explains CPG. The entire video is about 14 minutes long and can be viewed on our GG homepage. Now, when we look at these inverted 5-spot well patterns, we can also think about combining them. So you can see here in map view 4 inverted 5-spot well patterns combined with injection wells in the center and production wells at the corners. And so you basically have a power plant in the center of such a well pattern. This is just one example. We've looked into combinations thereof. We're simulating also the surface piping network and the power plant at the land surface to optimize the CPG power plant performance, particularly with respect to levelized cost of heat or electricity. So this was an introduction to CPG. Now I'm going to go to some results. And for now, we're restricting ourselves to heat and electricity results for a CPG, and then in the next section we will look at benefits to CCS by adding CPG to CCS. So here, first off, is a listing of our peer-reviewed journal publications in CPG, starting out with our first publication in 2011. With Jimmy Randolph in mind. So Jimmy, again, was the PhD student at the time in Minnesota with whom I co-invented this, and also Tom Keene, who joined shortly thereafter. He's on the next publication. And later on, when this is online, this presentation, you will have more time to look at these in red, the annotations, what these publications are each about. But essentially from the beginning in 2011 till last year, we published on various aspects of CPG. On the left, you can also see, again, a link to this video, and also the most important points about CPG, which is that it combines CCS with geothermal energy extractions. It, under base case conditions, at least it doubles the geothermal power generation compared to using water, else being equal. It still stores all of the CO2 eventually, permanently or geologically, because the CO2 that's being produced is re-injected along with the CO2 stream that comes from the capture facility. It basically subsidizes CCS with heat and electricity production and revenue, and later on we will see it will also benefit CCS in other ways. And it is what I call a true CCUS technology, because it does both U and S. So it utilizes the CO2 as an energy transport fluid, and it stores all of the CO2 subsurface. So in the next few slides, I will show you some of these publications, not all of them, mainly just the results, just to give a little bit of an impression what so far we have found out about CPG systems, and then what we're looking into now and what the CPG Consortium is doing. So this is again the very first CPG publication in Geophysical Research Letters by Jimmy and myself. And what we did here is we looked at inverted 5-spot well patterns on one time for EGS and enhanced geothermal systems or petrothermal systems. And we calculate using water and CO2, and we calculated what the overall permeability is. So in the center, you have an injection well, in the corners a production well, and you can calculate, of course, on a fracture-based system what the permeability is. And then we then use this exact same permeability, but as a porous medium that's not fracture dominated for CPG's calculation. So using CO2 to extract geothermal energy, and then we compare the two. And the result can be seen here. So you have the heat extraction rate in megawatt thermal over time. And down here you can see when you have a porous medium reservoir, a hydrothermal system, and all of these systems have a permeability of 50 millidarcy, and how much energy you can get out over time. And then if you have a CO2 EGS system with different fracture spacings here, but also 50 millidarcy or 5 times 10 to negative 14 meters squared permeability overall, you get these varying amounts of energy out here. And then finally, once your fracture spacing essentially goes to 0, you end up with CPG, which is basically a porous medium reservoir, like a hydrothermal system that, however, stores CO2 and is a CCS system as well. And there you get these 2 to 3 times power out. And this is for our base case. So all these reservoirs are 2.5 kilometers deep and so on, so which you can see on the previous slide. This was so far just for thermal power output in megawatt thermal. And then we started simulating quite a long time ago also the power generation, electricity generation. So we have the CO2 come from the emitter, it goes down, basically CCS, and then it comes back up, is expanded, cooled, condensed, and then goes back down again. So in a no heat engine cycle, this looks like that. You have a pressure increase on the pressure enthalpy diagram. You have a pressure increase from 1 to 2, that's going down your injection well with the CO2. From 2 to 3, the CO2 gets heated up, as you can see here. Then from 3 to 4, it is being produced to the land surface. And then from 4 to 5 is actually the expansion in the turbine. And from 5 to 1, when it goes through the vapor dome, and it ends up again at the injection wellhead, and then it self-injects as liquid CO2, since it's on the side of the vapor dome over here. So this is a power cycle, a heat engine, and a typical fossil fuel power cycle, a nuclear power plant power cycle would look something like this. And over here you have a CPG power cycle, the direct CPG system. So there's no binary loop or anything like that, or organic Rankine cycle. So the CO2 is directly expanded here. And you can see that all these components in a normal power cycle show up here, but that actually, interestingly, as I said a moment ago, the injection well down from 1 to 2 is doing the job of the compressor that you have before you put the heat in. So going from 1 to 2 over here. And then the geothermal reservoir providing the heat energy is here, which is normally, like say in the coal-fired power plant, the burning of the coal, and so on. So this is quite interesting to see this comparison. We simulate CPG entire systems, entire cycles, by simulating in various simulators like TUF2, CMG, Moose, and so on. And the power plant we simulate with engineering equation solver. We have semi-analytic solutions for the wells, and then we also develop our own simulator like Tango that I will mention later on, with which we couple all of these, or we use MATLAB for the coupling. So here you can see now a result for the electric power output of a CPG system. And what you see here on the right-hand side is a graph for a reservoir transmissivity in millidarcy meter on a log scale on the x-axis, and depth of the reservoir on the y-axis. This whole thing is for our base case, so not all of it is for base case, but the temperature gradient is base case of 35 degrees Celsius per kilometer. Surface temperature 15 degrees Celsius, approach temperature of 7 degrees Celsius. And also we had 2.5 kilometers deep, 50 millidarcies, 300 meter thick reservoir. And for the water version, we use an organic Rankine cycle in a binary loop to compare it. And the contour lines are the electric power output in kilowatt for CO2 in the brownish colors and water in the black colors. And the base case is the star here for that reservoir transmissivity here. And what you can see here is if you just go a little bit to the right of the star to just slightly higher transmissivities, then we have a crossover of the water and the CO2 case. And right at this crossover, we generate 3.2 times as much power with CPG compared to using water as the subsurface heat extraction fluid, all else being equal. And what you can also see, of course, electricity generation increases to the upper right. So the deeper the reservoir is and the higher the transmissivity is. The other thing is that right around here, where these contour lines are more or less on top of each other for water and for CO2, if you're beyond on this other side, then water is actually the better energy extraction fluid than CO2. And if you go to the other side, so all of this region here, CO2 is generating much more or extracting much more energy from the subsurface. However, being in the upper right corner is rather unlikely, not impossible, but rather unlikely, because you have to have really deep reservoirs. You can see here 5,000, 6,000, 7,000 meters. And at the same time, they would have to have very high transmissivities. And of course, the likelihood of having highly transmissive reservoirs at great depths is quite low. So we're typically in this region where CO2 outperforms water. And this is also a result from another publication where you can also see CPG is this here, what I call it a yellow line, and subsurface brine with an organic Rankine cycle indirect system that's here blue. And what you see is that for lower reservoir permeabilities, that you get quite a bit more electric power out of CPG compared to water, all else being equal. But at very high reservoir permeabilities, they're more or less the same. And if you go to even higher ones, then you would see this crossover that I just showed, and water would be better. So in this publication, Adams et al. In 2015 in Applied Energy, we also show how what the net power looks like for water-based systems versus CPG systems. So what you see here is net power in blue, I draw your attention to the two columns on the very right, which show essentially that you have normalized here 0.34 and 0.2 megawatt electric versus in CPG direct system, which are the only ones we consider at this point. It's again this 2 to 3 times more for this is again for the base case as stated up here. So we then have several more publications. I'm going to go through these rather quickly, also because you can later on go to the presentation online and then read and stop it and then read this. Just want to point out then that our geothermal publication in 2020, we show that we can get more power out by water that is being dissolved in the CO2 in the production well, exsolving out, and that's an exothermic reaction, so that gives more power. We also have a study here, this is by Justin Ezekiel and others, where we show that a CPG can be added on to form an enhanced gas recovery operation and how much power comes out of that. So here already the results showing the gas saturation and how much CO2 comes out. So we first simulate the conventional natural gas recovery, then enhanced gas recovery, and eventually CPG. And then the electric power output of the whole system. So this is in this publication that you see up in the upper right. You can read up on this in more detail. This is in Applied Energy. Then we also have a study where we show here by Mahmoud Hefni, my group, and others, where we show CPG after enhanced oil recovery. And this is in particular for Gulf of Suez. where we did we got samples from this depleted oil reservoir, took them to Switzerland to the synchrotron, developed a network model that you can see right here, and then did CPG simulations from the pore scale to the reservoir scale to really see how the CPG operations operate in a depleted reservoir. And yeah, so once you do this, so you simulate the CO2 injection and then eventually also the production of CPG and how the CO2 plume spreads. By the way, and a very important point is that the CO2 plume grows and grows because the CO2 again that we produce, we inject. So there's more and more CO2 coming from the emitter being captured. So the CO2 plume still grows and all CO2 is still sequestered, and eventually can calculate how much electric power comes out of that system. Then in 2021, we have a study where we show where we did parameter analysis. I won't go into details here either, but I just want to emphasize this because this study is really showing how the power output now varies as you go away from the base case. And you can see here in the upper right corner a table of power output in megawatt electric. And this is for different temperature gradients, 20, 35, 50 degrees Celsius per kilometer, different reservoir depths, different permeabilities, different thicknesses of the reservoir, and also different radii of the injection to the production well in this axisymmetric reservoir model. And of course, as you are to the lower right within each of these boxes, or overall to the lower right, you get a lot more power out than to the upper left, where you essentially get no power out. And that, of course, is because to the lower right, you have greater depths, greater temperature gradients, greater permeabilities, and greater radii or sizes of your reservoir. We also did another sensitivity analysis. This is again by Justin Ezekiel here in Energies, where we looked at the sensitivity of CPG compared to EGR or conventional natural gas recovery. And what really matters the most. And so non-surprisingly, the reservoir temperature matters the most for CPG, but also, of course, the well diameter and the ambient temperature is extremely important. Then also we looked into using CPG as a subsurface energy storage system. So this is a paper that we published in Energy Conversion and Management in 2022, where we add a shallow reservoir to a deep reservoir. And so you can then, when there's too much electricity available by solar or wind, then you can move the CO2 from the shallow reservoir into the deep reservoir by using that electricity. And when there's not enough electricity on the grid, then you can produce it like in a regular CPG operation, except for you bring it back into the shallow reservoir, the CO2, sorry. And so you can do this, plus you can actually have a regular CPG operation, which is the red line here, superimposed, if you like. Which can make sense under certain conditions. And so this provides a grid scale, very large scale energy storage system that actually can store energy from hours to seasons. And what we show in this paper here is that with relatively little additional costs, you can turn this CPG system in a CPG-F system, where the F stands for flexible, so that you can do all of these things. And then, of course, in sedimentary basins, you have quite often successions of reservoirs from shallow to deep. And then here, I just want to say that in this publication, we look at how CPG can support wind and solar power in renewable heavy electricity systems. So in the future, the power grids will have a lot more solar and wind power online, as we all know. And we need a lot of energy storage, as I showed a moment ago, but also dispatch power to basically kick in when there's not enough solar wind power. And of course, it's nice if this dispatch power can be renewable as well, like geothermal energy. And CPG then can provide that. So that's publication on that. And then finally, our latest CPG publication here is in the journal Energy. And in this one, that is the first author is Christopher Schifflechner from Technical University in Munich. And what we did here is we looked at what kind of requirements there are for the surface power plant system and what kind of turbines need to be built. And I just want to point out here that second bullet point, CPG can be applied in a wide range this is from the conclusions, a wide range of subsurface settings ranging from solar information to depleted oil and gas fields. And our techno-economic analysis indicates a large potential application field for this technology, estimated several hundred gigawatt electric, translated to a sizable market for CO2 equipment. So this is of interest then for power equipment manufacturers. So if there are more and more CPG systems going online in the future, then there will be a sizable market, or there should be a sizable market for CPG power equipment going forward. All right. So now I come to a few slides only about how CCS benefits from CPG being added to it, which is basically always the case. I mean, that was the idea that Jimmy Randolph and myself and Tom Keene had in 2009, that if there's more and more CCS happening in the world, that we could maybe make some good use of this geothermally heated CO2 by generating power. And so, as I said earlier, we have, of course, the advantage of generating highly efficiently electricity, or also heat, if you will, and this is right where the CO2 is being captured, or at least where it's injected, which could be somewhat further away. And so, of course, you can use this electricity and heat for the CO2 capture utility if it's not too far away, but also for the injection for the compressors or injection pumps. So that's this slide here. But then there are several other benefits for CCS, for adding CPG to CCS. One is that we cool the reservoir by running CPG operations. And so this means that that the density of the CO2 increases and the pore fluid pressure decreases. And this means that we can essentially store more CO2 or the same amount of CO2 safer. So that's what the upper left is supposed to show here, that you see a density phase diagram for pressure and temperature for CO2. And as you reduce the temperature here and the pressure by taking heat energy out, you can store more CO2 under same pressure or same amount of CO2 at lower pressure. Also, the maybe below next one is you can also increase the storage capacity with CPG by adding more of these producers that only CPG needs and not necessarily CCS. And this increases or improves your sweep, and so you can make better use of the CO2 reservoir. And this can be a rather significant effect, as you can imagine, because you can use much more of your reservoir, unless, of course, your CO2 happens to be spreading radially nicely outwards from your injection well anyway. Right, I mean, this middle one and the top here is about clean power. That's what I mentioned earlier, that CPG can provide. Then we have a CapEx improvement. We have flexibility to convert producers to injectors when we add CPG to CCS. So the CPG producers could be converted to injectors later on. We have reduced injection well redundancy, and end of CPG life producers repurpose as CCS injectors, sustain CCS injection capacity level, and we can have dual use of wells, protection well data, MMV cost savings. And also what's also quite interesting is that if you have only intermittent CO2 injection, for example, at Aquistore in Canada, then what they observed there is that there can be quite a bit of salt precipitation, because whenever they stop CO2 injection, because the CO2 is being sold to Weyburn for enhanced oil recovery, and then what happens if you stop CO2 injection is that you have brine backflow towards the injection well, and you can get salt precipitation, which reduces your injectivity index. And last but not least, public acceptance. Most people seem to really like the idea of geothermal energy extraction or renewable energy, and are not necessarily very happy about CO2 sequestration at a location. And so with CPG, you're doing both. And so we've heard quite a number of times already that it's nice to have geothermal energy usage added to CCS for public acceptance reasons. Of course, there are also some challenges with CPG. So lower temperature CO2 turbines are needed. High pressure CO2 cooling and condensing require dedicated development. We're looking into this right now in the CPG Consortium. Produced fluids need to be treated before reinjection, and also the regulatory support or framework often has to be changed, because the permits are usually only for CO2 injection and storage and not for taking it out again. This we believe is not that big of a hurdle if CPG is truly wanted, and that seems to be the case. So I just have a few more slides left here, and I want to talk here about the CPG Consortium before having one slide conclusion. The CPG Consortium, and first I'm going to talk about phase 1, is something that we started 2 years ago, and the objective of the CPG Consortium is to demonstrate the potential and technical feasibility of CPG to enable final investment decisions or financial investment decisions for FIDs on subsequent commercial scale projects. And as we're also investigating a field demonstration in the CPG Consortium of CPG, the point or the objective of that is to de-risk subsequent commercial scale projects to enable their FIDs with a focus on CPG specific risks. So let's first look at phase 1 that's ending next month. And so here, first of all, is the CPG Consortium. So you can see that here's again the CPG technology with the CO2 being captured and then injected with a compressor and then heated up in subsurface, being brought up, expanded, and then re-injected back into the reservoir, and electricity is being generated and sold to the market or used in the CCS operations. And we have the consortium research team as a project in my group here. And we have currently in the CPG Consortium, besides us, ETH Zürich in the lead, my group, we have Shell as a partner, Petrobras, Alterra Energy, and Holcim here in Switzerland. And also it's supported the consortium by the Swiss Federal Office of Energy. And then we also have an external consortium research team, so University of Leoben, University of Calgary, and Technical University of Munich. And the consortium research team, my group, looks like this, so you can see that here. And also we have a website which you can find under this link or QR code as well. Just a quick overview. So I was just talking about phase 1. So this started 2 years ago and is ending now, roughly speaking. And then we're going into phase 2. And this is something that we're setting up right now. So if anyone here on this call is interested in phase 2 of CPG, please do get in contact with me. I'll announce this in a moment as well. In phase 1, we did a site screening, and we also developed our techno-economic simulator, which is called TANGO. That stands for Techno-Economic Analysis of Geoenergy Operations. In phase 2, we will investigate the feasibility study, concept optimization and select, and technology development. And this is supposed to last also 2 years. Phase 3 then will be the demonstrator itself. So this is about field de-risking of commercial development. So TANGO, as I said, is our simulator that we developed, Techno-Economic Analysis of Geoenergy Operations. And it combines reservoir simulations with wellbore flow simulations, surface power plant simulation, and economic simulations, and then is wrapped with an optimization code so that one can, for example, simulate or determine under various scenarios the lowest levelized cost of electricity for a combination of these parameters, and also including economic parameters, all kinds of values. For example, what is the discount interest rate and things like that. And aside from native models for all these four, we also can outsource, so to say, simulations to other simulators like CMG, Moose, and so on. And also wellbore flow simulators and surface power plant simulators and economic simulators. Of course, the user will have to have licenses for these other simulators, but the coupling is done. It just requires, of course, to have a license for other simulators in addition to the Tango license, of course. And when with Tango, we developed Tango because there was or is no other solution out there that can provide this. So I mean, GEDM or Geofires were not or are not not really up for exactly these CPG simulations, techno-economic ones. We are also expanding the capabilities to all geothermal systems and also CCS systems and even completely other power systems. So and like district heating and things like that. So with Tango, then we can determine the potential of CPG, and what we mean by that is these cost-ordered cumulative capacity expansion curves here. And what it shows you is for different locations or for the assets of our partners in the CPG Consortium, what is the cumulative power output on the x-axis, typically in gigawatt, and what is the cost of that? So as we add reservoirs to these lines, what is the levelized cost of electricity for each reservoir? And then this is also, this is not cumulative, but this is then showing for each of these reservoirs that get added and adding more and more cumulative power, what is for each reservoir the LCOE. And then also the green curve shows for each reservoir, and also in a cumulative fashion, how much CO2 is required, or more positively phrased, how much CO2 gets geologically sequestered in the process. And this is what we mean by determining the potential of CPG. So basically how much power comes out, electric or heat, in this case electric, and how much CO2 is stored geologically, and what's the cumulative power installation, which is the x-axis. And so the low-hanging fruit would be to the very left of this curve. And this is just an example. And of course, I didn't put any numbers here. But in the CPG Consortium, we're doing this again for the assets, the reservoirs of the consortium research partners. Yeah, so, and then phase 2 is coming up now. We are currently having discussions with, of course, the partners who are in phase 1, and also with new partners from various places. Some of them considered being in phase 1, but for various reasons did not join at the time, but are now interested in joining now. Some are completely new, and like I said, some are the previous partners. And in phase 2, we do CPG optimization and monetize increased CO2 storage capacity, development optimization, daily and seasonal power variations, so between day and night, and also summer and winter, to really see also how does the CPG system perform off-spec. So sometimes, always, I mean, you have to design your power plant, your turbine, your cooling for an optimum case, and this is not always the case because of day and night, heat rejection temperatures, or because your reservoir is decreasing in temperature or your flow rate is decreasing. And so the question is, how can you optimize this off-spec performance? And yeah, the objective here is in phase 2, identify CO2 sequestration and geothermal development value improvements with novel geothermal CCUS technologies and computational workflows. So we have 3 focus areas. One is CPG itself, one is novel geothermal CCUS technologies, and one is novel computational methods. So essentially our Tango simulator to further improve that, to really do even faster a large number of realizations of different scenarios to calculate what is the economics of an entire CPG system or other system, also hydrothermal or hydrothermal before CPG. Right, so this is phase 2, and this brings me to the conclusions. So first of all, CPG broadens the geothermal resource base by more effectively extracting more geothermal energy. It also, when you add CPG to CCS, it still results in 100% CO2 sequestration, and is thus what I call a true CCUS technology. So it's not just CCU or CCS, but it's both, since all CO2 is sequestered and you're still using it, the CO2 as an energy extraction fluid. The CPG supports CCS in multiple ways, as CPG provides heat and electricity. It generates revenue. It increases the CO2 storage capacity by reducing pore fluid pressure, increasing density of CO2, and improving CO2 sweep. It provides directional control in the CO2 plume, provides continuous CO2 injection, and provides redundancies as CO2 producers can be converted to injectors. It may help with public acceptance of CCS, and it can result in synergies with CCS monitoring. CPG can be expanded to include short-term to seasonal grid-scale energy storage by adding a shallow reservoir and a sedimentary basin that is quite reasonable to expect that there is such a reservoir at shallower depth. And CPG supports the energy transition in multiple ways by 1, providing a renewable energy source, 2, by supporting CCS, and 3, providing dispatch power and energy storage if the shallow reservoir is added, to support only intermittently available wind and solar power, which is going online much more in the near future worldwide. And then finally, the CPG Consortium was founded 2 years ago. Phase 1 is concluding now as we speak, while phase 2 is being planned now as well to start later this spring, or transition from phase 1 to phase 2. And the Integrated Industry Academia JIP CPG Consortium is designed to pave the fastest way towards real-world CPG implementation. So I'm again providing here in the upper right the QR code and the link to the CPG Consortium website. And if you're interested in joining a CPG Consortium phase 2, please contact me. You can see my email here, sarm@ethz.ch. And we can then present more what we're planning, but also to hear what your needs are with CPG or CCS or geothermal in general, and if we can help with any of that in the CPG Consortium. So with that, I thank you for your attention, and I'm happy to take questions.
Martin, for that presentation. I think there's plenty of interest on CPG. And we have something like 24 questions to go through, so we'll try our best. A few questions on the startup of a CPG project, of a potential CPG project. Do you envision this as something that transitions from a hydrothermal geothermal system? Is there how long does it take for, say, a hydrothermal system to be considered CPG, or what volume is needed? For what volume of CO2 injection will be needed to, say, support something like a 1 megawatt pilot plant? Do you have rough numbers for that?
That's a really good question. So indeed, I mean, we're also thinking about converting hydrothermal systems over to a CPG system, or CCS and CPG systems. But originally the idea was and still is to go where the CCS is already happening, or where CO2 is naturally underground in reservoirs already, and to basically add CPG onto already existing CO2 sequestration or natural CO2 reservoirs. So in that sense, there's no conversion, but it's just adding the geothermal energy extraction loop on top of a CCS loop, not loop, but CCS CO2 injection. But yeah, nonetheless, we are also thinking about basically geothermally de-risking CCS by first running geothermal operations, and then also you can learn a lot about the caprock integrity without having to inject any CO2. And you can already test your reservoir, and you can already extract energy before you start CCS operations. So that would be a geothermal operation before CCS, and then to that, once CCS comes, it could be converted to CPG. Now, how much CO2 do you need? We also have a paper out of the several papers that you saw on that one slide, and that paper is about what the CO2 saturation in the pore space needs to be surrounding the CO2 production well inlet. And Buckley Leverett, 1941, is basically all about a gas versus a liquid entering the production well. And you can see that for different relative permeabilities, it's slightly different, but that you need something like 45% CO2 saturation in the pore space surrounding the production well inlet to produce after an initial startup phase mostly far above 90% CO2, and therefore in the production well, and therefore can produce the CO2 without getting liquid loading. So this is, answering a question. You need you can place a production well where you have, as soon as you have 45 or 50, let's say, percent CO2 saturation in the pore space surrounding the future production well inlet.
Thanks for that. I have several questions here on chemistry, corrosion, and scaling issues. Do you anticipate that there will be heavy corrosion or scaling when using pure CO2, or is this going to be an issue if there is even a very small amount of fluid in the system?
Yeah, as for that, I'll go out of my presentation mode here just for a second, because we are looking into that. So my GG group here has a reactive transport laboratory, and we look at all kinds of chemical reactions for geothermal, for CCS, for CPG. And we're conducting exactly these experiments for CPG, and we just have a paper out. And I asked Nicholas Ranchel-Horato, who is in my group and who is the first author of this paper, to provide a slide here. And yeah, I mean, let's see if I can now do the sharing here. Okay, so now you should be able to see it. So we run in our lab these experiments. The paper just came out this month in Energy and Fuels, and we look at wet versus dry CO2. So when you have dry CO2 where there's no water dissolved in the CO2, then yeah, we don't see or expect any reactions. But the big question has always been what happens when you have wet CO2, because after all, if you inject CO2 into brine, you get some water dissolving into the CO2, making it wet. And indeed, we see some more reactions, and we see some transport here of ions. But, and this is the important part, is the effect is rather small. So this is about the reservoir. Now, in the wells, of course, you can get corrosion, and you can also get reactions in the power equipment and so on. There it has, and we've been discussing this for many years now with manufacturers of equipment, And the bottom line or the overwhelming agreement is that yes, it makes things more expensive, but it's not a deal breaker. So in other words, you can use much more expensive but still doable stainless steel wells or composite materials to handle the corrosion issues. So for the most part, we do not think that that scaling corrosion will be a huge problem. And in fact, we expect it to be more of a benefit to use CO2 to actually have much less of at least the scaling issues compared to water-based geothermal systems.
Yeah. Let's move on to the more mechanical side of things. Have you looked into the geomechanical effects of injecting CO2 at high pressure? Are there any risks of fault activation or seismic activity? And on the engineering side, what pressure ratings are needed for, say, pressure vessels or tubulars to support a CPG system?
Okay. Yeah, it's also a really excellent question. 1 second as I go back to the presentation. So just the conclusion slide. Yeah, so we are involved in mechanical rock mechanics experiments and simulations as well. We have not conducted dedicated CPG or specific CPG rock mechanics experiments yet, but overall, the when you add CPG to CCS, we expect that the rock mechanics situation is actually improving. As I said earlier, by taking out the heat energy, you reduce the pressure, the pore fluid pressure, and so your cap rock integrity is heightened because you take this energy out, because you reduce the pore fluid pressure. So this is so CPG goes in the right direction. It rather improves the safety than or increases the safety than compromising it. There are, to be fair, I also want to mention, that there are concerns, for example, by adding production wells that, of course, you're puncturing the cap rock more frequently. But on the other hand, these are dedicated CPG or CO2 production wells, not very old, abandoned oil and gas wells from decades ago. And so as long as you do it right, it should be possible very much possible to add wells puncturing the cap rock and still have them not leak. It's just a matter of properly installing them. But for the most part, I mean, the important message is that CPG is very much expected to increase the safety because of the reduction in pore fluid pressure when you take energy out of the reservoir.
Okay, that's good.
This is, by the way, also why. Yeah, just 1 second. This is also this geothermal de-risking of CCS by taking out geothermal energy before you even start CCS operations. You're also having this effect. You're having this effect even ahead of time before injecting any CO2 by reducing the temperature, reducing the pore fluid pressure. So you're basically priming the reservoir for later CO2 injection.
Okay, this question is somewhat related as well. How do you ensure that the CO2 plume flows from the injector to the production well? Like how do you contain the CO2 within the fracture system?
How do you contain it? I mean, the basic idea, as you see here in the upper right, of course, is that you have at significant depth, you have a cap rock underneath which you have a reservoir, full-fledged, naturally permeable reservoir, could even be a depleted oil or gas reservoir that has a known cap rock that is sealed, that's tight. So again, I mean, the whole idea of CPG really is to add it to CCS, and CCS being done wherever, many places where there are depleted oil and gas reservoirs or brine reservoirs. So it's really just making usage of these CCS reservoirs that are, however, at least 2 kilometers depth. And there are a number of them. And if the interest is there to do CPG, then you're actually looking for them like we do right now in Switzerland. We're in the middle of a study that's part of the CPG Consortium funded by the Swiss Federal Office of Energy to look specifically for deep reservoirs from 2 to 5 kilometers depth for CCS in Switzerland, so that later on CPG can be added to those. And yeah, and so you are greater depths and you have a cap rock, or more likely have a cap rock, particularly if it's a gas reservoir, depleted gas reservoir.
Okay, then I have a couple of questions here regarding abandoned oil wells or depleted gas reservoirs, which the questions go on different directions. Do you see CPG as a way to repurpose depleted gas fields for geothermal, or do you see that technology as something that can, say, revitalize the production of a gas reservoir?
Yeah, the former. So it really is that you have more likely that you have a depleted gas reservoir that can then quite nicely be used, first of all, for CO2 storage, but also then for CPG. Yeah, so it would be the former.
Okay, then. Yeah, we're running out of time, so maybe we can wrap it up with some question that's a little more general. So we have a lot of questions regarding pilot projects, demonstration projects, and you're working on it, right? Like, but it's been a long road to get here, and there's still plenty of work that needs to be done before we even get to that point. So, what can you say what have been the insights throughout this whole process, and what would you say have been the major hurdles for deploying such? I mean, it's a very different technology from what you know of in geothermal.
Yeah, yeah, it's really been quite a journey, I would say, and leading, up to this demonstration site that we're planning. And yeah, it's the major hurdle is that we're combining here a subsurface technology with power generation, and we have power utilities being interested, oil and gas companies, CO2 sequestration operators, and so on. And I would say the biggest hurdle really is to combine these very different groups of people with their very different backgrounds and also their risk tolerances and expectations, and to make it all work in a combined way. And I'm very happy that we have the CPG Consortium now, where there are people in my group in the CPG Consortium who come from the oil and gas industry, who have done research and development in oil and gas companies and development and so on. But also we have, of course, academics here in the group, and a very diverse team in this CRT, in the consortium research team. And so it's now really possible to, I would say, in the CPG Consortium to combine all of these different backgrounds and experiences to finally make a CPG a reality in the real world. And to start out with a demonstrator that then later on can be converted or used or expanded to a commercial scale CPG operation.
I'm definitely looking forward to the progress that your consortium makes, and hopefully you'll have the pilot project in a couple of years, and we're very excited for it. So I think that's we still have a couple of questions, but these I will just have to forward these questions to Martin, and then the presentation itself will be uploaded to our YouTube channel. So if anyone's interested, you can just wait a couple of days for that. And then I think that's it. Thank you, Martin, for that presentation.
Yeah, thank you very much again for having me. And yeah, again, everyone out there who's interested in CPG, please get in contact with me and we can go from there. Thank you.
Then, and while I still have a couple hundred of you here, ThinkJ Energy will be publishing its annual top 10 geothermal countries and also the updated numbers for the global geothermal power installed capacity in a couple of days. So watch out for that. It's always a very exciting time for us. So once again, happy weekend to everyone. Thank you, Martin, for the presentation. And this is another episode of the Focus on Geothermal webinar.
Thank you.